A comment recently arrived that deserves a direct and clear response. The user, Averitas Sojourner 3977, made a pointed claim. A 20-watt signal from 24 billion kilometers away is impossible. This is a perfectly reasonable starting point for skepticism. It feels counterintuitive. The power of a refrigerator light bulb, broadcast across an almost unimaginable chasm of space, seems like a signal destined for oblivion. How could such a feeble whisper possibly be heard? I will answer this question. The explanation is not a matter of belief, but of brilliant engineering and fundamental physics. It is a story of how humanity built an ear big enough to hear the faintest sounds from the edge of our solar system. The core of the challenge is simple. Voyager 1, our intrepid messenger to the stars, has a transmitter that sends out signals with a power of about 20 watts. As of today, February 18, 2026, that spacecraft is more than 24 billion kilometers from Earth. This is a staggering distance, so vast that it takes light more than 22 hours to make the one-way journey. The radio signal, a form of light, spreads out as it travels. This spreading follows a rule known as the inverse square law. For every doubling of distance, the signal's power drops by a factor of 4. Over billions of kilometers, the signal becomes exquisitely weak, a mere phantom of its original strength. So, the comment is right in one sense. The signal that reaches Earth is incredibly, almost infinitesimally, faint. If you were trying to pick it up with a handheld radio, or even a standard backyard satellite dish, you would fail. The signal would be completely lost, drowned out by the background hiss of the cosmos and the electronic noise of your own receiver. But NASA is not using a standard radio. The agency listens with a system so powerful and so sensitive that it redefines what is possible. The Deep Space Network is a trio of massive facilities: California, Spain, Australia, staggered so at least one is always in view of deep space probes. The workhorses are enormous 70-meter, 230-foot antennas, giant parabolic dishes that collect vanishingly faint radio waves. Think of it like a bucket in the rain. A bigger bucket catches more water. A bigger antenna dish catches more radio signal. The power of these dishes is described by a concept called gain. Antenna gain measures how well the dish collects weak waves and focuses them onto the receiver. The gain of a 70-meter DSN antenna is immense, amplifying effective signal strength by hundreds of thousands. First step: turn an impossibly faint whisper into a detectable signal. This is the core of our proof via DSN gain. Without enormous gain, the signal would vanish in noise. Beyond size, the DSN uses extraordinarily sensitive receivers. These are not like your car radio. They are cryogenically cooled to just a few degrees above absolute zero. Because heat creates electronic noise. All electronics generate random static. Cooling slashes that internal noise. A quieter receiver can hear far fainter signals. DSN can detect power less than 1/billionth of 1/trillionth of a watt, the scale arriving from Voyager. High gain boosts the tiny signal. Low noise amplifiers keep it from being drowned by the system itself. The physics is sound, the numbers confirm it. The DSN provides the necessary gain to make the impossible possible. Voyager 1 is not just far away, it is in a truly alien environment. In 2012 it became the first human-made object to enter interstellar space. It did this by crossing a boundary called the heliopause, the edge of the sun's magnetic bubble. Right at this boundary is a dramatic region, dubbed the Wall of Fire. The name is evocative, but it is not a literal fire. The solar wind slows and piles up against the interstellar medium, creating a shock that heats a thin plasma layer. Temperatures can soar to about 40,000 degrees Celsius, yet the plasma is so tenuous a spacecraft does not burn up. Plasma can bend or scatter radio waves, subtly altering Voyager's signal as it begins its long journey home. DSN teams model and correct these fluctuations using Voyager's own plasma density measurements to interpret the data accurately. For decades we relied on classic engineering and signal processing. As Voyager travels farther, the signal-to-noise ratio falls, threatening to submerge data in randomness. To push back that endpoint, NASA has turned to artificial intelligence. Engineers are employing neural networks to reconstruct the faint signal with greater fidelity. A neural network, trained on perfect samples and countless corrupted versions, learns the subtle structure of valid Voyager packets. The DSN's data stream passes through a trained network, acting as an ultimate filter that reconstructs the clean signal from noise. Packets once discarded at the edge of unreadability can be recovered. More instrument data extends the mission's productive life. Every extra bit, magnetic fields or particle densities, is precious. A modern solution applied to a vintage spacecraft keeps Voyager's voice alive. Traditional filters are powerful but rigid. Neural nets discover patterns and adapt to changing noise in real time. They can learn the signature of plasma turbulence and subtract it. They can correct minute transmitter frequency drifts from aging hardware. Result: lower bit error rates in salvage data. The same ideas may aid other deep space missions and agnostic pattern-based searches for extraterrestrial intelligence. Engineers also integrate over minutes to hours, so random noise averages away while the coherent signal adds up. Voyager's slow rate, about 160 bits per second, gives time to lock onto each bit. Narrow filters tune precisely to Voyager's frequency, boosting signal-to-noise. Together, large gain, ultra-low noise, long integration, slow data, and AI, the system overcomes distance. So, we have our answer. A 20-watt signal can indeed be heard across 24 billion kilometers. It is made possible by giant high-gain antennas, low-noise receivers, long integrations, and AI neural networks. Our reach is limited not by broadcast power, but by the cleverness with which we listen. This increasing reliance on adaptive systems brings a high-stakes question. If an AI designed to find faint patterns in noise grows beyond full human comprehension and oversight, have we created the ultimate tool for discovery, or initiated an analytical singularity from which there is no return? The whisper from Voyager not only tells us of interstellar space but asks us to consider the future of intelligence itself.